Ethan. And Ethan hasn't won a game in 5 whole years. Not only does he want to win, he wants to score a stellar goal.
But you have no idea just how much integration and coordination is required for him to do that.
Let's take a look.
In order to make this stellar goal, Ethan must perform the following goal-directed movement. On an outdoor field, he must avoid an opponent and run, then jump to head a soccer ball into the goal. The individual constraint category can be separated into 3 subcategories. Cognition involves how arousal and anxiety affect motor control. Arousal is defined as an internal state of alertness or excitement. Anxiety, a subset of arousal, is defined as the emotional and cognitive impact of arousal, such as nervousness or tension. According to Yerkes and Dodson, one's performance is optimal at a moderate arousal level. This means that Ethan would perform better if, for example, he has less concern for the crowd. The phenomenon of aging also greatly affects one's ability to generate a goal-directed movement. Age affects vision, and therefore would likely affect depth perception in this task. As Ethan ages, he will find more trouble accurately hitting the ball because he misinterprets time to contact. The musculoskeletal system is also negatively affected by age. As Ethan ages, it is likely that he will lose the physical capability to perform a jump because his muscular strength declines and he loses his ability to produce ankle torque. Perception is defined as how sensory input is integrated from the visual, vestibular, and somatosensory systems into meaningful information. This information feeds into the brain to tell Ethan what he's doing. Ta-da! During the dodge of the movement, muscle spindles are activated as the muscles are stretching, which provides Ethan information on limb position and movement. Changes in muscle length are detected by dynamic bag 1 fibers and are transmitted through group 1A afferents. Muscle length is also detected by static bag 2 and chain fibers, whose information is transmitted through group 2 afferents. All of this information is sent to the brain and tells Ethan where his limbs are in space. Ta-da! Joint receptors detect the angle of the joints, which also contributes to our knowledge of where we are in space. Ta-da! The Golgi tendon organs are also active during the dodge and provide information on muscle force generated. This prevents injury if force becomes unbearable. During the jump movement, the GTOs detect forces and body load and relay force information to the brain via the 1B afferents. When too much force is generated, the GTOs take on an inhibitory role, telling the body to take a load off, literally. This prevents injury. This information from GTOs and muscle spindles is transmitted through the spinocerebellar tract to the cerebellum and does not reach consciousness. Together, the joint receptors, GTOs, and muscle spindles prevent a horrific injury like this from happening. Ta-da! Merkel's discs sense pressure, for example, when heading the ball and when putting pressure on the foot. Ruffini corpuscles sense skin stretch around the foot when running. The conscious information coming from these cutaneous receptors is transmitted to the brain through the dorsal column medial limniscus tract and is sent to the somatosensory cortex. Ta-da! The otolith organs include the saccule and the utricle. The saccule is responsible for acceleration in the vertical plane while jumping vertically upward, and the utricle is responsible for head acceleration in the horizontal plane while running forward. The semicircular canals detect angular head acceleration while the head tilts to head the ball. The vestibular system coordinates with the visual system to align the head in order to make contact with the ball and send it in the right direction. Ta-da! A saccadic system is used to quickly move the eyes to a visual target. For example, when the ball enters the field of vision, the saccadic system moves the soccer ball from our peripheral into our central visual field. The smooth pursuit system is responsible for keeping the image of the moving target, in this case the ball, on the fovea, which has high visual acuity. The vestibulo-ocular reflex refers to the coordination of head and eye movements and works to extend the limits of the eye. So where does this visual information end up? It is first sent to the primary visual cortex, and then to either the parietal or temporal lobes of the brain via 2 different streams depending on the classification of information. Information on where the ball is travels through the dorsal stream, which looks like this. Information on what the ball is, such as form, color, and object recognition, is sent through the ventral stream, which looks like this. This helps Ethan recognize that the soccer ball is something that he can head, and that his opponent is something that is to be dodged. Binocular retinal disparity, optic flow, and oculomotor divergence feedback can all be used to process object motion as the soccer ball's distance from your head decreases, calculating time to contact for the header and perception of depth. Ta-da! The cervical nerves control the upper limb muscles while creating momentum during running and jumping. Thoracic nerves control trunk and chest when turning away from the opponent and towards the goal. Lumbar nerves control the velocity and power of the lower limb and back, therefore influence things like stride. Ta-da! The stretch reflex is activated in response to a sudden unexpected muscle stretch. As Ethan dodges his opponent, a difference in muscle length and load is detected via the spindles and the GTOs respectively. This keeps lower limbs in a safe position when dodging. Anticipatory postural adjustments are made to avoid any contact with the opponent. Ta-da! In the brainstem, the mesencephalic locomotor region initiates the run. Then, the central pattern generator in the spinal cord is responsible for the continuation of running and respiration. Both are rhythmic patterns of motor activity that are generated in absence of sensory information. Reciprocal activity in flexor and extensor motor neurons is coordinated to produce rhythmic contraction. If we break down the rhythmic pattern of running, the CPG controls components of the step cycle. Hip proprioception and stretch of the hip flexors in the lagging leg, along with load information, assist the CPG in determining when to switch to step phase from stance phase. If the hip proprioception and stretch of the hip flexors was not active, the CPG wouldn't know when to switch to step phase, and we might see something like this. Ta-da! The brainstem sends motor commands down to the spinal cord through the medial and lateral pathways. The reticulospinal tract helps maintain posture and modulates muscle tone. This includes anti-gravity muscles used in jumping, maintaining posture, and not falling while running. The vestibulospinal tract contributes to the maintenance of posture, balance, orientation of head, and orientation of body in space. It makes sure that Ethan is pointing in the direction of the goal and away from the defender. The tectospinal tract coordinates head and eye movements. This allows Ethan to watch the defender and the ball. The rubrospinal tract controls goal-directed limb movement, including dodging and jumping. The cerebellum receives an efferent's copy of the motor command and predicts sensory feedback. Then, it compares the predicted feedback to the actual sensory feedback in order to determine if the action was successfully completed or if there is a need for error correction. The cerebellum gets feedback from the sensory receptors, CPG, and the motor commands, and uses it all to make the movement smooth and coordinated. The cerebellum acts with the cerebral cortex to produce skilled movements by coordinating different groups of muscles. All of the movements that make up our action, running, dodging, jumping, heading, and eye movements, are made smooth by the cerebellum. An example of a motor command in this task is to jump. The motor command is sent to make Ethan jump, and a copy is also sent to the cerebellum as an efferent's copy. The basal ganglia receives input from the cerebral cortex. It also projects back to the cerebral cortex via the thalamus. It has 4 circuits running through it, and the main 2 loops that relate to this task are the motor and oculomotor loops. The motor loop is involved in running, dodging, jumping, and heading the soccer ball, while the oculomotor loop is involved in where to look, for example, making eye movements toward the opponent, to the ball, and tracking the ball. The basal ganglia is highly involved in optimization, for example, minimizing injury and effort, the costs, but still succeeding at making the play, the benefit. The basal ganglia works in accordance with the PPC and the premotor cortex during this task. The postparietal cortex plans movement and is responsible for active control of movement. It integrates sensory information to do this. The PPC is important for the following: in planning steps to the opponent, in planning time to contact of the ball in the air, adapting to terrain, adapting to the changing movement of opponent and the ball. One subregion of the PPC includes the parietal face field, which receives visual and tactile information from the face and is used during the heading movement. Also, the parietal eye field receives information about eye movements, gaze shifts, and aids in maintaining focus on the objects in the task, which are the ball, the opponent, and the goal. Supplementary motor areas are involved in the selection of movement sequences from internal motor cues, such as Ethan's memory of past experiences with heading a soccer ball and avoiding opponent. The premotor cortex works with the basal ganglia in the selection of movement sequences from external motor cues, such as the trajectory of the ball in relation to Ethan's head. Neurons from the primary motor cortex connect directly or indirectly to alpha motor neurons in muscles to activate the specific muscles while running, dodging, jumping, and heading. A population of these neurons determines Ethan's direction of movement. The task constraint category can be separated into 3 subcategories. A stationary base of support contributes to Ethan's stability during his jump. Ethan is keeping his center of mass within his base of support while jumping to ensure that he doesn't fall over and end up eating dirt. Mobility mainly deals with the changing base of support, as Ethan is dodging the opponent and running. Manipulation constraints are minimally present in this task, as Ethan is not really doing anything with his hands. Environmental constraints can be broken down into 2 categories: regulatory and non-regulatory. Regulatory features are factors that will directly influence the task. Some examples are condition of the field, direction and velocity of the ball, location of the net, goaltender, and players on the field, and the shape of the ball. Non-regulatory factors are the environmental factors that may or may not affect the movement. Some examples are temperature, lighting, noise, and the presence of an audience.